So in question 34, what we have is that we have a rock climber, and initially he's up at some height. So initially he's up here. But then what happens is, oh no, he falls, he slips and falls, and he just falls freely through the air, just as though he wasn't attached to anything at all. And he falls down until he's fallen through a distance of what I shall call h. And that distance that he falls freely for is 0.75 meters. But fortunately for him, after he's fallen from here down to here freely, once he gets to here, then his safety rope runs out of slack, and that begins to decelerate him and bring him to a rest. And it brings him to a rest once that safety rope has been stretched out by a distance that I'll call x. And let's suppose that we say that this position down here is 0 meters. So this is our reference level. So the height that he was up when he initially fell is just going to be the distance by which the string is stretched before he comes to rest, plus the distance through which he moved when he was falling freely. Now, what the question is asking us to calculate is how much is the rope stretched? So it actually wants us to calculate what this x is here. Now, I guess what we can use to figure this out is that there are a couple of forces doing work on him. What we want to do is to get an equation which involves this x that we're then able to solve. Now, there are a couple of forces doing work on him, as I say. Over the entire distance here, gravity is doing work on him. And over this distance here, the spring force is doing work on him. Another thing we can note is that initially when he slips and falls, so his initial velocity is going to be 0. The reason that he starts moving is that gravity does work on him and he starts being accelerated down by that. Now down here, where he comes to a momentary rest, he is also not moving. So his speed down here is 0 and his speed up here is 0. So although we have these two forces doing work on him over this distance here, the net work done on him as he goes from here down to here is just going to be 0, because his change in kinetic energy is going to be 0. So I think that probably would give us an equation that we could hopefully solve for this x. So let's think about that. So the net work done on the climber is equal to, so we say the net work done on the man during the fall, we'll say during his descent, is the work that gets done by gravity plus the work that gets done by his safety rope. And the work that gets done by gravity is, of course, just equal to the negative of the change in his gravitational potential energy. And the work that gets done by his safety rope is going to be the negative of the change in the elastic potential energy of this climber safety rope system. Since the man is initially stationary, and the safety rope brings him to rest, after he falls, the change in his kinetic energy is just 0. So by the work kinetic energy theorem then, what we can say is that the net work has to be 0, and that means that the negative of the change in the gravitational potential energy take away the change in the elastic potential energy also has to be 0. And so what is this change in his gravitational potential energy? Well, the change in the gravitational potential energy is going to be his final gravitational potential energy take away his initial gravitational potential energy. Now his final gravitational potential energy will just be 0 because he finishes up down at this reference level, so it's going to be 0 joules with respect to this reference level. And his initial gravitational potential energy is just going to be his mass times g times by the height above the reference level that initially is. So his initial height is going to be h plus this x. And now we have to take away the change in his elastic potential energy, or the elastic potential energy of this climber rope system. And so the final elastic potential energy then is going to be a half times the spring constant of his safety rope times by this x squared. Now when he initially starts falling, his safety rope wasn't stretched at all. So the amount of elastic potential energy stored in it was just 0. And so his final elastic potential, so his initial elastic potential energy was 0, and so we have this. So again, we have a few zeros, so we can cancel out minus signs here. And we get, this is mg h plus x. And then we have to take away a half k x squared. Now if we just expand out these brackets, we find that mg h plus mg x minus a half k x squared is equal to 0. And I guess we should note where m is the man's mass, and k is the effective spring constant of his safety rope. And we're given numbers for both of those. So we're told what those two things are, and so what we have here really is just an equation in a single unknown. Unfortunately, it's a little bit more complicated than what we'd usually have, because we have both an x and we have an x squared, and we also have a term with no x on it at all. So this is actually a quadratic equation in x, and since x is the thing we want to solve for, we're probably going to have to use the quadratic formula to solve this. Or alternatively, we could just plug this into Mathematica. So let's just write down what the quantities are. We have the spring constant is 1 times 10 to the 3 newtons per meter. The guy's mass is 86 kilos. And that h is 0.75 meters. So let's go over to Mathematica and get it to do the number crunching for us. So go over to here, and this is question 1034. So we have that his mass is 86. And let's just use the solve command. So we just type in our equation. And we have to tell it the variable that we want to solve for, which is x. And it might be a good idea, just in case I've declared x to be something else. Sorry, I want to clear x. Just in case I've already declared x to be something and it gets confused by that, I'll clear it out. And so if I entered my equation correctly, I think I have. So if we now just shift enter on that, yes, of course. I have not entered a quantified system of equations, so I forgot to put on my equals 0 onto the end. And so I find that the distance by which the rope stretches, so the amount by which this rope has been stretched before it brings them to a stand, is going to be 1.95 meters.